I want to talk about energy. Okay, so how energy impacts our lives, how we need to look toward different, better energy systems globally, and how we are energy systems, and I'm going to explain a few of them to you, are tied together by common physical, and is that better? Yeah. Physical and chemical phenomena that I'm going to describe, and how that all leads to wanting to make things really small. So if we make things really small, we can actually make better devices for converting energy into forms that we like to use them. I'm going to try to do all of this in 20 minutes, so let me get started. So as we all are aware, maybe some of us don't think about it that often, we depend heavily on energy. Everything we do really depends on energy. We use it for food, we use it for water, both purifying water and moving it around. We use it for transportation, it drives a lot of our industries, and so we rely extremely heavily on energy. We can agree, I think, and probably this is something you've heard about if you read any newspaper or follow similar talks like this. The global energy system is under a lot of stress. We have a lot of people on this earth. We have nearly 7 billion people, and it's growing. And if you even look at the current population, 2 billion people today do not have access to modern energy services, things that we take for granted. For example, being able to plug these projectors into the wall to get electricity. It's a big part of the U.S. economy. It's about 7% of the U.S. economy and spending related to energy. And this is already a little bit outdated. This number here, nearing 400 parts per million of CO2 in the atmosphere, it's actually already hit 400 parts per million of CO2 in the atmosphere. I'm going to explain why that's an issue in a moment. Okay, sorry, I should have had a picture on here before. Okay, so it is involved in meeting human needs, driving our economy. It impacts the environment very strongly, and it's tied in very closely with national security as well. Okay, so here's the Earth. I want to just give a couple of statistics that I think are very impressive. First is that every second, mankind consumes almost 1,000 barrels of oil, 93,000 cubic meters of natural gas, and 221 tons of coal. This is not every hour, every minute. This is every second. And these numbers are already probably growing from when I put this together. And the other really stunning fact is that if we have this trend of increasing energy demand globally, and if we want to maintain that trend that we've had over the last 60 years, continuing up to 2050, we would need to build every single day about 3 carbon-burning power plants, or 2 nuclear power plants, or if we want to do photovoltaics, which I would like to do, we need 10 square kilometers of photovoltaic modules every day to maintain that trend. And I should mention that these statistics come from a book that I use in a course I teach and have taught here at Stanford for sort of introduction to energy. Okay, I like to show this picture because it indicates what a popular form of energy is to us. It's probably the most popular, and that's electricity. It's really a favorite form. This is a picture of the United States at night, collected from a composite of satellite images from NASA. And you can see the entire United States is outlined just by the lights that we have on at night. Of course, lighting is just one use of electricity, but we love our electricity. We use it all the time. And the electricity used, this number may not mean anything to you in these units, but it's about half a terawatt. This was already a couple of years ago, which is a half a trillion watts. I mean, imagine what that is when you think about a 100-watt light bulb. We shouldn't be using 100-watt light bulbs anymore. We should be more like 10 or 20-watt compact fluorescent or LEDs. But that's a lot of electricity used. And the thing you might not have thought about electricity is that even though it's a favorite form, we all use it all the time, it is rarely a primary source of energy. There aren't that many primary sources of electricity. One is a lightning storm. You don't usually harness electricity from a lightning storm. So it's usually a secondary energy source, which means we need to take some other form of energy and convert it into electricity because we love to use electricity so much. So what is this initial source of energy that we convert into electricity? We have lots of different options and we take advantage of them. Nuclear is one, wind is one, sun is one, water is one. Niagara Falls, for example, water dropping down. We can take that energy and convert it into electricity. And the biggest one is chemical energy. When I say chemical energy, this is energy stored in chemical bonds, primarily in fossil fuels. So if we look at our world net electricity generation, most of the energy we use comes from burning of fossil fuels. So if you look, this goes out, this is projected. So if you stick to the two columns on the left here, which at least the first one, 2010, is real data, 2015 and onward is projection. But coal, natural gas, and a little bit at the bottom there, liquids, that's all coming from fossil fuels. That's the majority.
Worldwide or just US?
This is worldwide. Yeah, this is worldwide. Sorry, it's a little hard to read where it comes from. But it is from the US Department of Energy data. And you can see that the trend is going up. So a lot of this is coming from the burning of fossil fuels. We have some renewables. You can see that they're in green. Some of it's hydropower, which is another form of renewable. But the dominant part is coming from fossil fuels. And the problem with that is every time you take a fossil fuel and convert it to electricity, it generates carbon dioxide. Okay, and that carbon dioxide goes up into the atmosphere. The reason that's a problem is carbon dioxide is what's called a greenhouse gas. Okay, it absorbs infrared light, which is related to heat. And when you increase the concentration of carbon dioxide in the Earth's atmosphere, it leads to warming of the Earth. And I think there's been a lot in the news lately about global warming, so I won't mention more about that, except that it's a major concern. But it does other things too. All this carbon dioxide in the atmosphere, a lot of it's actually being taken up by the oceans. Okay, so it's a great sink of all this carbon dioxide. Some of it goes into the atmosphere, some of it stays in the oceans, but it increases the acidity of the oceans, and that's leading to its own set of problems that you don't hear talked about quite as often as global warming. So these are two big issues with carbon dioxide emissions. So where do we go from this dependence on all these fossil fuels? What I want to say is there's not going to be one solution. I'm not going to stand up here and say, oh, if we all just switch to solution A, we can solve this problem. It's a really complex problem. We use a lot of energy, so we need to have multiple solutions. There's not going to be one single technology that's going to work, so we're going to need a collection of them. One place we might look is renewable sources of energy. Okay, so energy that we can reuse, or is renewable, and turn that into forms that we like, such as electricity. And this is an interesting plot because it shows how much energy is available to us from these various renewable sources. I know some of you are looking, thinking that's a typographical error at the top. It says exergy. Okay, that means that's the usable part of energy. It's not a typo. And so you can look at these common forms of renewable energy: solar, wind, hydrothermal, tides, waves. All these things are renewable sources of energy. And the bars here show how much of that is available relative to this number that's kind of approximately what our current use is, which is 15 terawatts. So that's 1 on that plot. And this is on a logarithmic scale. Okay? So you can see that by far, several orders of magnitude more than we actually use today is available in solar energy. Wind is pretty good too, but it's down by quite a bit. Things like waves or tides, they're a lot smaller. So that's why there's kind of a big emphasis on solar, because that's just this vast source of potential energy that we can use to make electricity and fuels and things like that. So one of the things that I do is co-direct this Center on Nanostructuring for Efficient Energy Conversion. It's funded by the U.S. Department of Energy. And we think a lot about this problem, about how we can come up with different devices or methods of converting energy efficiently to forms that we like to use from renewable sources. And so this is one vision that we sort of thought about for a sustainable energy future. You see the sunlight, the sun is there in the corner, that's a big part of it. We can use something called a photovoltaic. This is a solar cell that can take that sunlight and convert it into electricity directly, so that's great. But the problem with that is you can only make electricity while the sun is shining. So you could be doing something with electricity and a cloud might go right in front of the sun, or even worse, it might turn into nighttime and then electricity goes away. So you have to come up with ways to store that electricity, and one common way that we're all familiar with is batteries, but there are other techniques too, like supercapacitors. There are ways to actually take that sunlight and directly make fuels that you can use to drive your cars, or fuels that you can use to eventually go back into electricity, and that device is called a photoelectrochemical reactor. That's the thing on sort of the top right. And other devices that are very efficient that can be used to go between fuels and electricity are called fuel cells, and those are shown there too. So what about all these devices? The interesting thing about those devices that I showed there, that all differ a lot, one's a fuel cell, one's a battery, one's a solar cell, they all depend on similar physical and chemical phenomena. Okay? So what do I mean by that? If you look down at the very small level, even below atom, they rely on the same processes. And what that process is the following, as it says there in the middle. Each one of those generates a positive and negative charge carrier. That can be something like an electron, it can be something like an ion, like a sodium ion. It moves that charge around, and then it recombines it. Okay, so they all have that same set of steps in common. And I'm going to show you an example, one or two examples you can believe in. Okay. So this is a photovoltaic. This is a solar cell. It takes sunlight and converts it directly into electrical energy. And the way that works is you have semiconductor materials, typically two of them, two types. What's called P-type, that one likes positive charge carriers, or positive charge carriers like that material, that's why it's P. And N-type is for negative type charge carriers. And so what happens in a typical photovoltaic device is the light comes in from the sun, and here's this step that I talked about. You generate these charge carriers. Okay, so you generate, in this case, what's called an electron and a hole. And now those charge carriers move around, I mentioned that step, and then they recombine and generate electricity, which is power, which you use to power up something like a light. Okay, so again, you generate these carriers, they move around, and they recombine. I can take something that's completely different, like a fuel cell, and I won't go into each of these steps, it's more complicated. A fuel cell takes chemical energy and converts it to electrical energy, and it does it by the same sets of processes. It generates charged species. In this case, it's things like, it's electrons, but it's also things like ions, like H+, protons. It moves them around, and then it recombines them. So we have these same steps in common. Why is that so important? The reason that's important is it gives us a clue to how we might be able to make all of these different devices better and more efficient. And one way that you can do that is to make things smaller. Okay, so I want to explain why would making things smaller make them more efficient. Because I only have 20 minutes, I'm going down to one point here. And one way that things get better when you make them smaller is, remember, you're always making these charge carriers, you're moving them around, and you're recombining. All that moving around involves a lot of loss. Okay, so if you make things smaller, things don't have to move as far. And you can go back to this photovoltaic example, where if you generate, as it shows there, your charge carrier is something that's thick, far, far away from where it needs to go, this is treacherous out there for this charge carrier. It can reach all kinds of traps on the way and never make it to where it's collected to make power. Okay? If you make things smaller, like the image on the right, you have a much better chance of collecting those charge carriers and extracting electricity from it. So that's the sort of easy picture of why something smaller might be better. Okay, so now, with that in mind, small might be better. And when I say small, I mean really small, nanometer small. Okay, so 10 to the minus 9 meters. Okay. So this is called nanotechnology or nanoscience. Things are very, very small. And so if we go back to this vision for a sustainable energy future and you look at what constitutes a lot of these devices, even now, photovoltaics, fuel cells, batteries, they're already on the nanometer scale. A lot of them have really, really small components, and these are pictures of either theoretical or actual little particles and little things that drive these different devices. And going forward, we can do even better if you incorporate even more of these nanoscale type materials. Okay, so I want to give just one example of how we can try to make things smaller. And this is a project that we were working on over the last few years, which is related to solar cells. So we already know that we have to have something that absorbs light, generates charge carriers, moves them around, and recombines them. This is an example of what's called a thin film photovoltaic material. So we want to have a semiconductor that's not very thick to absorb the light. And this thing called CZTS is kind of complicated, but it's just one example. This is just one material, but any material has certain properties at which it absorbs sunlight or any part of the electromagnetic spectrum. And this one it absorbs in the visible. So you can see that in certain regions, say the blue parts of the visible light spectrum, it absorbs really well, but in the red it doesn't absorb so well. So what you need to do in a photovoltaic is you want all of the light absorbed by the time it gets to the bottom. In other words, you're throwing away some of that light. So that limits or dictates how thick that needs to be. And for something like this material CZTS, and pretty much every sort of best semiconductor we know of, it needs to be on the order of a few microns thick. Now, a few microns is smaller than the thickness of hair on your head. It's actually pretty thin, but to these electrons and holes moving around, it's kind of thick, and it leads to a lot of losses. So we'd like it to be even thinner than that couple of microns. We'd like it to be like that thick, on the order of tens of nanometers. Okay, now it's really hard to imagine absorbing all the sunlight in something that thin, but we have ways of trying to do that. And one way to try to do that is shown here. Okay? So we're looking to try to get what we call extreme levels of light absorption in very, very small amounts of material. And there's a structure here that we were trying to build, which has this sort of pink layer here, which is going to be very thin, has really interesting properties that it can absorb light well. We have below that a mirror, basically, a reflector, so that the light comes in, most of it's absorbed, some of it hits that reflector, comes back up, and the thing in between is this transparent space. Or that could be like air, but if we're actually making it, it has to be some other material that's transparent. And if we can design that right, with the right spacing, with the right mirror, and the right little pink layer there, which is a composite, we can, in principle, absorb all of the light in that structure. But the bottom two parts, this transparent spacer and the reflector, they don't absorb light at all. That's just a mirror and air. So all of the light, therefore, can be absorbed, in theory, in that very thin red layer or pink layer there. And that's what we tried to make. So this was shown theoretically that you could do this, and then we set out to try to build this sort of structure. It involved combining semiconductors or other types of materials with little metal particles, and that's what's shown here. So these are little gold particles. We didn't make these at Stanford. These were done with collaborators at a company, Hitachi Global Storage. And then we coat those little particles with a very thin layer of other material. And the best image is probably the one on the bottom left. Those are little gold particles, the dark spots, and they've been coated with whatever material we want. In this case, it's zinc oxide. And by changing the properties of that structure, how thick the zinc oxide is, how spaced out it is from that bottom mirror, we can change the color and how well it absorbs light. And so if you look at those images or the grid on the right, those are actually photographs of these devices that are very colored. Okay, the ones with the two stripes and the second and fourth down, those are, as we make very, very small changes to the film, on the order of just a few nanometers, we completely tune the properties. And so we took advantage of this to try to get this structure that could absorb almost all of the sunlight in that one layer. And we reached some success. So what we were able to do is show that we could absorb nearly all of the light, actually 93% of the light at a particular wavelength in the visible, in just the gold. And those gold nanodots, if you were to sort of melt them out and flatten them out, the whole thickness is under 2 nanometers. It's extremely thin. And in that very, very thin layer, we were able to absorb almost all of the light. So this sets kind of a new record for extreme light absorption. And where we're going now is putting semiconductors on that so that we can absorb the light in the semiconductor and make ultra, ultra thin photovoltaics. Okay, so let me conclude. Nanoscale materials are one way of making energy conversion devices more efficient. And I gave you one example of trying to make solar cells or solar absorbers with ultra-thin layers of light, ultra-thin layers of material. Just a quick set of acknowledgments. This was work carried out by a very talented group of postdocs, Carl Hagelin, Hamza Romney, and Isabel Kovan, between my group and a collaboration with the colleague Mark Rongersma, collaborated with Hitachi, and that's all I have. So thank you very much for your attention.